Hey everyone, we are presenter 6 from group number 3 and today we'll be discussing control surveys. Just to give you guys a heads up, these are the topics that we will be discussing today and there will be calculations involved, but it shouldn't be too hard. Just stay with us and we'll talk you through it. So my group mate Vince will start us off.
First, let's dive in the definition of terms. In control surveys, the following terms are commonly used. Baseline, one of the lines in a triangulation system whose length is precisely measured and its true direction determined by astronomical observations. It is usually located at the beginning of the triangulation system, and its length is used as the basis for computing the lengths of other lines of the system. Check base, one of the lines in a triangulation system whose length is also precisely measured and may be located at regular intervals or at the end of triangulation system. It serves as a check of triangulation computations involving lengths of lines. Trilateration, a method used for horizontal control surveys which is based exclusively on measured horizontal distances. It consists of a series of joined or overlapping triangles where sides are measured and that angles are computed. Now let's proceed to control surveys. Control surveying is referred to as the determination of the precise position of a number of stations which are distributed over a large area. For its applications, control surveys are used to establish coordinate systems for mapping. Moreover, control surveys are used to establish baselines from which field surveys can be performed. The established stations of the system serve as the basis for originating or checking other subordinate surveys for engineering projects such as topographic and hydrographic mapping, planning, designing and layout of highways and railroads, and delineation of property or political boundaries. Control surveys can be divided into two general types, which are laid out in the form of net covering areas to be surveyed, which are horizontal control and vertical control. Horizontal control surveys over extensive areas generally establish geodetic latitudes and longitudes of stations. Plane regular coordinates are subsequently computed from these values. The main objective of horizontal control survey is the establishment of a network of triangulation sections. The field procedure used in horizontal control surveys include control by traversing, control by triangulation, and control by trilateration. With traversing, a series of horizontal distances and directions are observed to connect points whose positions are to be determined. This procedure is generally less expensive and can be extended in any direction. When a large area is to be surveyed, and where the methods of traversing would not be expected to maintain a uniform high accuracy over an entire area, triangulation is specified. Triangulation surveys consist of networks of geometric figures with almost all of the angles measured directly in the field and with relatively few of sides measured. With trilateration, in this procedure the lengths of the sides of a series of triangles are measured and the angles are computed from the lengths. Trilateration is the most accurate of the three methods because distances are measured more accurately than angles. Next is the vertical control. A vertical control survey determines elevation with respect to sea level. These surveys are also used as a benchmark upon which other surveys are based and a high degree of accuracy is required. These surveys can be done alone, but are often done in conjunction with a horizontal control survey. In vertical control surveys, the main objective is the establishment of a network of reference benchmarks. Vertical control surveys may be run either by differential leveling, trigonometric leveling, barometric leveling, GPS, and/or photogrammetric methods. Differential leveling is determining the difference in elevation between two or more points without any regard to the alignment of the point. It is best run over level or gently sloping terrain. It is also the most accurate and widely used method. Trigonometric leveling is an indirect method of leveling in which the difference in elevation of the points is determined from the observed distances measured in vertical angles. Trigonometrical leveling is commonly utilized in topographical work to find out the elevation of the top of buildings and etc. Also, it may be used to its advantage in difficult terrains like mountainous areas. Barometric leveling methods are particularly suited for work in rough countries. where high precision is not desirable. These are also used to reduce the slope distances to horizontal when measured electronically. The principle used in barometric leveling is that the elevation of a point is inversely proportional to the weight of the air column above the observer. With GPS, it provides surveying and mapping data of the highest accuracy. GPS-based data collection is much faster than conventional surveying and mapping techniques, reducing the amount of equipment and labor required. Lastly is the photogrammetric methods. It refers to the ground control targets or photo-identifiable points occurring within the area of a project. Maps are prepared from photographs taken from ground or air stations. Thank you.
Good day, ladies and gentlemen. I'm Jezreel Vincent T. Apiar, and we will now tackle about triangulation. So in this type, it consists of networks of geometric figures with almost all of the angles measured directly in the field, and with relatively few of the sides measured. When a large area is to be surveyed, and where the methods of traversing would not be expected to maintain a uniform high accuracy over the entire area, then triangulation takes place. Each of the calculated distances is then used as one side in another triangle to calculate the distances to another point, which in turn can start another triangle. This is done as often as necessary to form a chain of triangles connecting the origin point to the survey control in the place needed. So keep in mind on some of the following functions or uses of triangulation. First is to establish accurately located control points for plane and geodetic surveys of large areas. Next, establishing accurately located control points in connection with aerial surveying. Third, accurate location of engineering projects such as center lines, terminal points and shafts for long tunnels, and center lines and abutments for long span bridges. Let's take a look with this triangulation net example. As you can see in the picture, this is the world's first large-scale mapping of an entire country in the year 1846, completed by the Irish Ordnance Survey under Lieutenant Colonel Thomas Colby. The survey, at a scale of 6 inches to 1 mile, was primarily a townland survey and not detailed enough for a proper valuation, so a more comprehensive survey was then completed. The mapping was done by triangulation, and by creating a series of primary triangles, sightings were taken between stations using theodolites. Much of this work was done at night to reduce the distortion caused by heated air. In order to complete the network of triangles, the length of one leg of one triangle had to be measured. The leg chosen was along the shores of Lough Foyle, and this measured distance is known as the baseline. The accuracy of the measurement of the baseline was paramount as it set the scale for the whole survey. The measurement of the baseline began in the year 1827 and was carried out under tenting to avoid fluctuations in temperature. The bars were mounted on tripods at a total distance of 7.89 miles, which included crossing the River Row, was completed in November 1828, after 60 days of measurement by 70 men. Now, let's proceed to triangulation systems. It consists of a network of connected triangles which adjoin or overlap each other, the vertices of which are marked points on the Earth's surface. It is essential that the length of one side be measured directly, aside from the interior horizontal angles, to make the possible calculation of the remaining triangle sides in the net. So there are geometric conditions to be fulfilled in triangulation system. These are the following. First, the sum of interior angles should be the quantity of 2n-4 times 90 degrees, where n refers to the number of sides of the figure. Second, if all the angles are measured at the station, their sum should be 360 degrees. Lastly, the length of sides calculated through more than one root should agree. We also have triangulation station, which refers to the vertices of the triangles in a triangulation system. There are different geometric figure arrangements used to form the triangulation systems. The first one is chain of triangles, which is used when a narrow strip of terrain is to be surveyed. It involves a minimum of angular measurements and calculations for the amount of area covered. The next one is chain of quadrilaterals, which is the most commonly used triangulation system. This affords an excellent system since the various combinations of sides and angles can be used to compute the lengths of required sides, and checks can be made frequently. Each figure is composed of two pairs of overlapping triangles, which gives the maximum opportunity for the distribution of angular errors. The third one is chain of polygons. It is composed of a group of triangles having within a station, which is at a vertex common to all the triangles. When areas that are very wide in proportion to their lengths are to be surveyed, then pentagonal or hexagonal figures may be economical. And lastly, the chain of polygons with diagonals. It is very essential that only well-shaped figures used in triangulation systems, since the errors in measurement in lines and angles, no matter how small, will affect the computer values. Now let's take a look at the advantage and disadvantage of the fourth. First, in chain of triangles. It is simple, rapid, and economical. However, the downside is that it is the least accurate method, considering that it lacks certain checks to balance small errors, which are common even in the most careful work. For the chain of quadrilaterals, it is the most accurate system as the number of checks are more. However, it is also the most expensive system to use, but it's still desired knowing that it provides the highest accuracy, so it's still worth it. Now, both in chain of polygons and chain of polygons with diagonals, it is also accurate as the desired number of checks are more, in comparison to the chain of triangles. Now, let's have a sample problem. In a topographic survey, 3 triangulation stations, A, B, and C, are sighted from a point P. The distance between the stations are AB is equal to 500 meters, BC is equal to 350 meters, and CA is equal to 450 meters. At P, the angle subtending AC is 45 degrees, while for BC is 30 degrees. If the azimuth of AC is due north, find the azimuth of PA. The first thing that you need to do is to make a diagram, as you can see on the left side of the slide. Since there are already given angles which are 45 degrees and 30 degrees, you need to get the distance of AV and BV from the triangle ABV. So, in order to get the value of the two, we need to use the sine law. So for AV, we have AV over sine 45 degrees equals 500 over sine 105 degrees. AV sine 105 degrees equals 500 sine 45 degrees. Divide both sides by sine 105 degrees. So the distance of AV is 366.025 meters or 366 meters. The same process for BV. We have BV over sine 30 degrees equals 500 over sine 105 degrees. So the distance of BV is 258.819 meters or 259 meters. So for the next step, we need to get the angle of A using cosine law. Given that A is equal to 350 meters, B is equal to 450 meters, and C is equal to 500 meters. We have 350 squared equals 450 squared plus 500 squared minus 2 times 450 times 500 cos A. Negative 2 times 450 times 500 cos A is equivalent to negative 450,000 cos A. You need to add 450,000 cos A and subtract 350 squared on both sides. So we have 450,000 cos A equals 450 squared plus 500 squared minus 350 squared. Divide both sides by 450,000. So we have A is equal to arc cos times the quantity of 450 squared plus 500 squared minus 350 squared all over 450,000. So angle A is equal to 42.8 degrees. To get the angle needed for us to solve the azimuth, we need to use the sine law and substitute the given values, including the values solved in the previous slide. But before that, we need to subtract 42.8 degrees to the given value or angle, which is 30 degrees. So we have 12.8 degrees. In order to get the distance of CV, we still need to use the cosine law. CV squared is equal to 450 squared plus 366 squared minus 2 times 450 times 366 cos 12.8 degrees. Therefore, the distance of CV is 123.46 meters. Using the sine law, we have 123.46 over sine 12.8 degrees equals 366 over sine gamma. Sine gamma 123.46 equals 366 sine 12.8 degrees. Divide both sides by 123.46, so the answer is 41 degrees. Since we already have calculated the angle needed, then we can solve the azimuth of PA. Recall it was stated in the problem that the azimuth of CA is due north, as shown in this diagram. So we already got the angle, which is 41 degrees, and 45 degrees is also given. What we need to do is to get the azimuth of AP first. So the sum of the two angles, which is 41 degrees and 45 degrees, is 86 degrees. Recall that one of the geometric conditions to be fulfilled in triangulation system is that the sum of all the angles that are measured in a station should be 360 degrees. Therefore, since we already have 86 degrees, so the azimuth of AP is 274 degrees. Now, since we have the azimuth of AP, then we can calculate the azimuth of PA, where 274 degrees is subtracted by 180 degrees. Therefore, the answer is 94 degrees.
So, good morning everyone. I am Raymond Adlawan and I will be discussing to you the topic on the adjustment of a chain of triangles. So, there are a number of geometrical conditions which the angles of any triangulation system should fulfill. For instance, the shape of a triangle may be completely determined by two angles alone. Therefore, the measurement of the third angle is superfluous. In surveys, it is not very probable that the three measured angles would all add up to 180 degrees. In this case, a correction needs to be applied in order that the final angles of each triangle would add up to 180 degrees. This should be the first set of conditions imposed on the corrections if computed results are to be determined correctly. Moreover, the angles of an independent figure where two or more roots are available in determining unknown quantities would not be geometrically consistent all the time. This imposes a second set of conditions on the corrections used. Additionally, in an independent figure, when a length can be computed by more than one root, the angles must be adjusted so that the computations of each root will give the same solution. This constitutes a third set of conditions called the side condition. Since all measured angles are affected by the errors of measurement, these angles will never somehow meet all the conditions perfectly. It is therefore for this reason that there is a need to adjust observed angles so that only the accurate values may be determined. It is also logical to say that only corrections that have the greatest probability of being true corrections should be used. There are two basic objectives in adjusting measured quantities in triangulation, namely the removal of inconsistencies and the prevention of error accumulation. The adjustment of the data may be undertaken by the exact method called the method of least squares or by the approximate method of least squares. So adjustment by least squares is the most frequently used estimation procedure in surveying. This method is based on the theory of probability and is one which simultaneously adjusts the angular and linear measurements to make the sum of the squares of the residuals a minimum. So residuals are the differences between the most probable value and the observed values. This method will give the most probable correction that will satisfy the required angle and side conditions. Furthermore, this method is useful in determining the best obtainable values from a given set of measurements and for determining the relative worth of different determinations. This method may also be used in tracing the sources of various errors that affect the measurement and consequently increase the accuracy of the result. This adjustment is one of the best and most rigorous for traverses and triangulation systems. It is, however, somewhat complex and requires lengthy calculations. Approximate method. This is rather a simple and convenient method used for adjusting angles and sides of triangulation systems which are of lower orders of precision. There are two types in the adjustment of chain triangles, namely station adjustment and figure adjustment. So, station adjustment. The goal of this adjustment is to make the sum of the angles about each station, that is, the sum of the interior and exterior angles of that station, equal to 360 degrees. If the sum is not equal to 360 degrees, an adjustment is made by determining the difference between 360 degrees and the sum of the measured angles. The resulting difference is then divided by the number of angles about the station. The correction is then added algebraically to each angle. Figure adjustment. This adjustment uses the values obtained from the first adjustment. Therefore, this must be performed only after the first adjustment is finished. For this process, the sum of the interior angles of each triangle should be 180 degrees. In adjusting, the three angles of each triangle are added together, and their sum is subtracted from 180 degrees. The difference is then divided by 3 and then added algebraically to each angle. It is assumed that in both station and figure adjustments, the angles were measured with equal precision. So, sample problem. For the given chain of triangles shown in the accompanying figure and tabulation, perform station and figure adjustment by the approximate method. So, this is the figure for the sample problem. So, first, we are going to solve for the station adjustment. As you can see, the values of the angles are already given. All we have to do is to solve for the sum of the angles about each station, solve for the correction, and finally the adjusted values. So let's look at the figure once again so that we will have an idea of what we are about to solve for. Since the angles involved in station adjustments are the angles that are about the station, then we are going to solve for the angles for station A, which are angles A, B, and C. For station B, which are angles D and E, and so on. From the figure, we can logically say that the angles about the station must sum up to 360 degrees. Once again, we must take note that the sum of the angles about each station must be equal to 360 degrees. And that is for station adjustment. So now we are going to solve for the angles about station A. To solve for the sum, we simply add the observed values of angles A, B, and C. Now we have 360 degrees, 0 minutes, and 15 seconds as the sum. We will now proceed with solving for the error. In solving for the error, we subtract the sum of the observed angles from 360 degrees. Take note that the calculated sum of the angles must be the subtrahend, and the fixed value of 360 degrees must be the minuend. So now the error is negative 15 seconds. We will then solve for the correction. To solve for the correction, we will divide the error by the number of angles observed, or the number of angles that are about the station. In this case, there are 3 angles about the station, which is station A. So the value of n is 3. Dividing the values, we get negative 5 seconds as the correction. Finally, we will solve for the adjusted angles. For the adjusted angles, we will call them angle prime. So for angle A, we will call it angle A prime or simply A prime. It is important to remember what these angles are called because they will be used later on in solving for the figure adjustment. Now, to solve for the adjusted value of A prime, we add or subtract the correction to or from angle A. So since the correction is negative, then we subtract the value from the angle. So 5 seconds is subtracted from the value of angle A, which is 240 degrees, 21 minutes, and 0 seconds. We now have the value of A prime, which is 240 degrees, 20 minutes, and 55 seconds. We then repeat the same process in solving for B prime and C prime. After that, we will do a sum check to verify that the adjusted angles sum up to 360 degrees. In this case, our adjusted angles actually sum up to 360 degrees, as it should. So we will then input our computed quantities to the table provided. So next, we will proceed with station B. So we are going to look at the figure once again. So for station B, only 2 angles are involved, which are angles D and E. So angle D and E. We just repeat the process in solving for the sum, error, correction, and adjusted angles. So first, we get the sum by adding the observed values of angle D and angle E from the given table earlier. And then we solve for the error by subtracting the sum from 360 degrees. And then we get the correction by dividing the error by the number of angles involved or that are about the station. So in this case, there are only 2 angles involved. So the value of n is 2. And then we divide negative 4 seconds by 2, so we have negative 2 seconds as the correction. Finally, we then algebraically add or subtract the correction to or from the angle to get the angle prime or the adjusted angle. So for d prime, we subtract 2 seconds from the observed value of angle d. So we have 301 degrees 34 minutes and 47 seconds. And for e prime, we do the same process, subtract the correction. Since the correction is negative, we subtract it from the value of angle e. And so finally, we then do a sum check to verify that the adjusted angles sum up to 360 degrees. So once again, we then input our calculated values to the table presented earlier. So the process is just the same for all computations for each station. Therefore, we just repeat the process until we fill out the table. So the station adjustment table looks like this after repeating the process and solving for the adjusted angles for each station. So this is now the station adjustment table after solving for all the values. Next, we will be solving for the figure adjustment. So the table for the figure adjustment looks like this. As you can see, we are now solving for the adjustment as a triangle and not as a station anymore. So we have triangle ABC, ACD, CDE, and DEF. To further visualize these triangles, I will present the figure once again. So this is triangle ABC, and this is triangle ACD, and triangle CDE, and DEF. For clarification, the order of the letters in labeling the triangle may be interchanged. So you may call it triangle ABC or triangle BCA or CBA, for as long as it coincides with the label that you placed or that was provided on the table. So if this is triangle CBA, then you can also call this triangle CBA. So for figure adjustment, we must take note that the sum of the interior angles in each station should equate to 180 degrees. If this is not satisfied, then we will do the adjustment. Let's consider triangle ABC first. So let's look at the figure once again. Triangle ABC. So the interior angles involved are angles C, E, and F. In getting the sum of the angles, we add the values of the respected adjusted angles, meaning we get the sum of the prime angles from the first step, which was the station adjustment. So we get the value of C prime, E prime, and F prime, and then add them up. So the sum is 180 degrees, 0 minutes, and 25 seconds. We then get the error by subtracting the sum from 180 degrees. Again, take note that the sum is the subtrahend and the fixed value of 180 degrees is the minuend. So the error is negative 25 seconds. To solve for the correction, we once again divide the error by the number of angles involved. In this case, triangles always have 3 interior angles, so the value of n will always be 3. Now, notice that the correction has a decimal value. Since the error is not divisible by 3. In this case, we will round down the correction for 2 angles and round up the correction for 1 angle, meaning we will use negative 8 seconds as the correction for 2 interior angles and negative 9 seconds as the correction for 1 interior angle. To further illustrate, let's look at the process of solving the adjusted angles. The adjusted angle will now be called angle double prime. So as you can see here. So for C double prime, we subtract the correction from C prime. So our correction is a negative value. So we subtract it from C prime. So 59 degrees, 10 minutes and 0 seconds minus 8 seconds is 59 degrees, 9 minutes and 52 seconds. For E double prime, we subtract 8 seconds from E prime. Now, notice that in F double prime, we subtract 9 seconds instead of 8 seconds. This is what was meant by using negative 8 seconds as the correction for two angles and negative 9 seconds as the correction for one angle. As you can see, C double prime and E double prime used negative 8 seconds as the correction and F double prime used negative 9 seconds. This is actually done to avoid having decimal values for the adjusted values, because if we use negative 8.33 seconds as the correction for all angles, then the sum of the adjusted angles will either have an excess or will lack a value of 0.01 seconds. Although this error is very minimal, it would just be better to avoid such. Also, it is important to take note that the correction is applied arbitrarily. Therefore, you may use negative 9 seconds as the correction for C double prime and negative 8 seconds as the correction for E double prime and F double prime. As long as only one angle uses the rounded up value, or in this case negative 9 seconds, then it would be okay. We then input our computed values for the given triangle into the table that was presented earlier. So next we will solve for the next triangle, which is triangle ACD. So provided with a figure once again, we can say that the angles involved in triangle ACD are angles B prime, G prime, and M prime. So next, we simply repeat the process. We solve for the sum of angles B prime, G prime, and M prime first. Then we solve for the error, which is 180 degrees minus the sum of the prime angles. And then we solve for the correction and apply the round up and round down process. After that, we solve for the adjusted values or the adjusted angles. Once again, we will be using positive 11 seconds for two angles and positive 12 seconds for one angle. We also have the freedom to choose which angles gets the correction of positive 12 seconds since the correction is applied arbitrarily. We then do a sum check to verify whether the sum of the adjusted angles or the double prime angles would equate to 180 degrees. Since it equates to 180 degrees, we can now proceed to inputting our computed values to the table. So here it is. Now the process of solving for triangle CDE and triangle DEF are the same. We simply repeat the process and input the computed values in the table. So finally, our figure adjustment table would look like this after solving for all the adjustments. Once again, we must remember that we cannot solve for the figure adjustment without solving for the station adjustment first. That is because the values of angle prime that are used in figure adjustment come from the computed values of the station adjustment. So that's all for the adjustment of chain triangles, and now we are going to proceed with the strength of figures.
Hey everyone, so I hope at this point you are still with us because we will be discussing the strength of figures now and what it is for. So we should all know that in planning out triangulation systems, it is possible to have various positions available for different station sites. So naatay lain-lain options kung unsa nga route ang ato ang gamiton, and the strength of figures will help us decide which figure or which route is the strongest route na pwede nato gamitin. So again, the strength of figure, in order to adopt the best shaped triangulation network, it is necessary to have a criterion of strength to the different figures that may be formed. So in its most basic term, the strength of figure is the criterion of strength that we will be looking at in choosing the best triangulation network. This criterion or index is denoted by the letter R. Okay, so let's remember, strength of figure will be denoted by the letter R. So is it important? The strength of figure should always be considered in establishing a triangulation system to maintain the computations within a desired degree of precision. So yes, it is important. It plays an important role in deciding the layout of our triangulation network. So how do we make a decision? When comparing different values of A, the stronger figure has a smaller value. This means it is the route with the least error, and we will know unsa ang kasabot ani na decision making later when we apply it na. The strength of figure will be dependent on the comparative sizes of the distance angles, the number of observed directions, and the number of trigonometric and geometric conditions to be satisfied for a particular figure. So right now, I know these are all just words to you guys, pero once we perform the calculations later, you will really see why the strength of figure is dependent on the distance angles, the number of observed directions, and the trigonometric and geometric conditions. So makita na natin na siya later when we see what the equation is in order to solve for the strength of figure. So for the equations, so we will be using the law of sine for this one. And I assume and I hope that you guys know how to use this already, diba? Sine A over A is equal to sine B over B is equal to sine C over C. And letters A, B, C are the sides of the triangle. And sine A, sine B, sine C are the sign of the angles, the distance angles. So kaning nga mga angles, guys, ang tawag natin nila is distance angles. Kasi diba, these are the distances between two stations, Station A and Station B, mo na ilang distance. And kani po, distance po na sa Station A and Station C. So, ang angle in between those distances are called distance angles. So, ngayon kailangan matag law of sine because later you will know that we will be given one known side and angles. So, para makita na to ang other distances sa ato ang chain of triangles, we can use the law of sine. The next equation, kini siya guys. So, mo ni siya ang ato ang equation nga gamiton for our strength of figure. Strength of figure is equal to F multiplied by this summation term here. So we will define this later. I alam mo ka-intimidate. I know it looks new to you guys, pero this is really easy once you know how to solve for F and once you know how to solve for this term here. So let's dive in. First, we have the strength of figure factor. So muna siya ang first term nata diri. If you can remember, diba, R is equal to F times atong summation nga term diri, nato siya summation nga term which we will discuss later. Pero ang first term sa atong strength of figure is F. And this is called the strength of figure factor. So muna siya ang ato ang first nga isolve ang ato ang strength of figure factor. So how do we solve for our strength of figure factor? F is equal to D minus C over D. Okay, so what is D and C? So D here is defined as the number of directions observed, not including the known or the baseline. And C is the number of geometric conditions to be satisfied. So as you can remember kaganina, diba, our strength of figure is dependent on the trigonometric and geometric conditions. So this is why it's dependent on that, because in order to solve for the strength of figure factor F, we will be using the number of geometric conditions to be satisfied. And kaning C, guys, dili ni siya makita sa atong figure. Ang D nato, actually later makita nato nga maihap ra na siya when we look at our figure. Pero ang C nato, di na siya maihap, i-solve nato na siya, and this is how we solve for C. So unsa maning N prime, S prime, N and S. So N prime is the number of lines observed in both directions including the known or baseline. S prime is the number of occupied stations. N is the total number of lines including the known or baseline, and S is the total number of stations. This term here, N prime minus S prime plus 1, these are the angle conditions. Muna siya ang angle conditions nga need i-satisfy. And ang N and ang S, muna sila ang parameters nga maka-give sa ato ang value or ang number sa side conditions nga need i-satisfy. So, the number of geometric conditions is the sum of the number of angle conditions plus the number of side conditions. And if we find our letter C, we will find our letter F. Kaya ang di, maihaparaman na nato na siya. Okay, so we have here our example, diba? So, example 4.1, we have here our figure. Kaning blue, guys, I'll just let you know. The blue line here is our known line, okay? So, our definition kaganina, diba, is this is our equation for F and this is our equation for C. So let's write down our values. Okay, so pila man ang ato ang D diri if not including the known and the baseline. That's 1, that's 2, that's 3. No, wala ni siya ilabot. So again, balik ka sa 1. 1, 2, 3, 4, diba? Kay directions man in both directions. So 1, 2, 3, 4. So our DDI is 4. So, ang atong D is 4. So, let's just write that there. 4. C is number of geometric conditions nga ato ang isolve. So, kailangan nato ang N prime, ang S prime, ang N, and ang S. Okay, so, pila man ang ato ang N prime. So, apil na ang blue. So, pila man kabuk ang lines nato. 1, 2, 3. So, N prime is 3. Ang S nato is the number of occupied stations, which is 1, 2, 3. Okay, so, ang S prime nato is also 3. And then, ang N nato, again, is 3, diba? And ang S nato is 3. So, now, kaibaw, 3. So, now, kaibaw na ta, unsa ang angle conditions and ang side conditions, diba? So, if we put that in our calculator, 3 prime, here we go, 3 prime na noon, N prime minus S prime. So, 3 minus 3 plus 1 plus 3 minus 2 times 3 plus 3. That will yield 1. Ang value man nato sa ato ang D is 4. So, 4 minus 1 over 4 is 0.75. Therefore, our strength of figure factor is 0.75. Diba guys, intimidating kayo siya, pero sa'yo na kayo siya. Okay, so, next example. What is our value sa ato ang D man diri? So, again, D is the number of directions observed. Walay labot ang blue line. Okay, so, that's 1, 2, 3, nya both directions, so balik ka sa tumagi, 4, 5, 6, 7, 8, 9, 10. So therefore, ang atuang D is 10. How about the number of lines observed? So N prime na to. Pila man ang atuang N prime? 1, 2, 3, 4, apil ning blue line, 5, and 6. Okay, notice nga walay station dira sa tunga. So this is just one line. So 6 ang ato ang N prime. How about ang ato ang S prime? Pila man kabuk stations? 1, 2, 3, 4. So easy, 4. And then ang N nato, we already know it's 6. And ang S nato is also 4. There you go. And that will yield an answer of 4. So input that sa ato ang F na equation. So our strength of figure factor is 0.60. Okay, you guys, so now we know how to solve the first part in solving the strength of figure, which is the strength of figure factor F, diba? And now, we will try to solve for the summation of delta A squared plus delta A, delta B plus delta B squared. So what does this mean? So delta A is simply the difference per second in the sixth place of logarithm of the sine of the distance angle A of each triangle in the chain used. And if delta B na siya, then sine of the distance angle B. And I know it's very intimidating to read, and I know that this is, again, these are just still words to you guys, but once we solve it, you will see literally what every word means in a sentence. And this term can be calculated using a table or using a calculator, just with our calculators. And I will show you first how to calculate it using the table, and then later we will solve it using our calculator. So I'll show you both these methods. But before we go into that, I want you guys to remember that distance angles are the angles opposite the known and the required sides of the triangles. And this is the table that we will be using. So ang first method, diba, is solving it using our table. So these values here are the values of sa ato ang summation or sa ato ang katong term. So muna siya ang values sa ato ang chain of triangles. So first example, for the chain of triangles ABC and BCD, determine the summation of values given the distance angles 33 degrees and 60 degrees and 30 degrees and 58 degrees respectively. So mo ni siya ang angle sa ABC and these are the angles for BCD. So this is our first triangle here and this is our second triangle. So as you can see, this is a quadrilateral and we divided it into two triangles. So that's why chain of triangles. So triangle ABC and triangle BCD. And this is our common side, diba? Obviously, mo dyan siya atong common side as you can see sa ato ang given na roots. Our first triangle is triangle ABC with first angle 33 degrees and second angle 60 degrees. And our second triangle BCD have angles 30 degrees and 58 degrees. So how are we gonna solve this? So first natong isolve using this table is ang first triangle, which is triangle ABC. So one triangle at a time, okay? So first triangle ABC, first angle nato is 33 degrees daw. Pero since wala man tayo 33 degrees because this is we only have 30 degrees and 35 degrees here. So we will be using both values because we know that 33 degrees is somewhere in the middle here, right? And then we go all the way down to 60 degrees because that is the second angle of our triangle. So how are we gonna solve that since we only have 35 degrees and 30 degrees and their corresponding values here sa nga nag-cross with 60 degrees. So how are we gonna solve that? So we know that 33 degrees is somewhere in the middle. So 35 degrees minus 30 degrees over the corresponding values of 14 minus 19. So that's what it says here. That's what we input here is equal to 35 degrees minus somewhere in the middle 33 over corresponding values of 35 is 14 and corresponding value of 33 is wala ta kaibaw. So that will be our unknown value which is x. And then we just shift solve that. I hope you guys know how to use shift solve in your calculators, but if you don't, then I will still show you. So 35 minus 30 over 14 minus 19 is equal to 35 minus 33 over 14 minus x. Okay, so how do we shift solve? We press shift and then we press solve. Simple. Then we solve. So it says x is equal to 16 now. Let's see if we are correct. We are correct. And then our second triangle BCD, we have angles 30 degrees and 58 degrees. So we see here, okay, naa tayo 30, easy. And then we go down, pero wala tayo 58. We don't have a value 58 here, but we know that 58 is somewhere between 60 and 65 and 55. We will do the same thing. Again, we perform this calculation in our calculators and then shift solve, we will get a value of 19.8. And diba, summation of triangles man to. So that means x plus y. X plus y. So that means our summation, sorry, this value here, kani siya, kaning 35.8, muni siya to ang squared. So this is our value. Summation siya. Because, why is it summation? Nganong na summation naman na siya? Because this x here, this is the value ani sa triangle A or sa triangle ABC. And this 19.8 is this value sa triangle BCD. So, x plus y muna siya ang summation value sa atong two chain of triangles. That should be the value sa atong second part sa term, which is kani. Where's my cursor? Which is kani. Diba? Kani siya. Muto siya atong value ani. And that's how we use the table for that part. Well, what if we decide to not use the table? What if we decide to use a calculator instead? So that is what we're going to do next. The same problem, but this time we will be using our calculators. So, okay, so I want you guys to really notice every word here. The difference per second in the sixth place of logarithm of the sine of the distance angle A of each triangle in the chain used. So, mao daw na siya ang delta A. Diba? Log of the sine of the distance angle. So, log sine And ang distance angle, which is, ang first na to nga distance angle sa triangle ABC, which is mo ang first na to i-solve, ang first distance angle nato is 33 degrees. So, log sine daw sa 33 degrees, diba? Logarithm of the sine of the distance angle A. Logarithm of the sine of the distance angle 33 degrees. Pero it's the difference per second. So, we will add. So, it will be the difference of log sine 33 degrees, 0 minutes, 1 second minus log sine of 33 degrees, 0 minutes, and 0 seconds. So, that is what this means. And we will see later what the sixth place of log of the sine means. Okay. So, muna siya ang ato ang equation for our first angle. And equation for our second angle will be this one. So, instead of 33 degrees, 60 degrees na ang ato ang istilat. And how are we gonna perform that in our calculator? So, I'll show you guys here. We will try to solve for the first angle. So, log sine 33 degrees, 0 minutes, 1 second, 2 parentheses. Okay, let's be really careful with this. We need 2 parentheses on it. Minus log sine 33 degrees, 0 minutes, 0 seconds, 2 parentheses is equal to 3.242. Okay, 3.242 daw guys, times 10 to the negative 6. So, do we have to write 0.0000003.242? No, because it says this is the difference per second in the 6th place. So, if that's times 10 to the negative 6, we will literally put 3.242 here. Okay, so therefore, ang ato ang delta A is 3.242. And our delta B, if we will solve it, is 1.2156 times 10 to the negative 6. We will just put 1.216. So, muna siya ang ato ang difference for 1 second, or delta A and delta B. And that's for our first triangle. And then, since we have the values of delta A and delta B, we will simply substitute them here. Okay? Is equal to 15.93. Let's hope this is right. 15.9. Okay, so now we have our x value. Remember, x value siya because this is the value of this one for our first triangle ra. Napagitay value gay nga ni for our second triangle. Diba? Kay chain of triangles man. So now we will look for the second triangle. Again, the definition. Difference per second in the 6th place of log of the sine of the distance angle. So, first distance angle nato is 30. Second distance angle nato is 58. Again, we will input this in our calculator and we will get the values 3.647. In our calculators, this should show 3.647 times 10 to the negative 6. So, we will input 3.647 and delta D nato will be 1.316. So, we have delta C and delta D. What do we do next? We input this in our formula. Delta C squared plus delta C, delta D plus delta D squared. So, we will input that in our calculators. So, it says 19.8 daw. Okay, we're correct again. So, now we have our second value. Ngay nga ni. So, ganina natay X, karon natay Y. And since we need the summation, so obviously, i-add na to. So, 15.9 plus 19.8, 35.7. I don't know if you guys can still remember, pero when we used the table, we got a value of 35.8. And when we used our calculator this time, we got the value of 35.7. So, obviously, dili gid siya exact, pero it's very close. Okay, so now we already know how to solve for the strength of figure because we already know how to solve for the strength of figure factor, which is the letter F, and we know how to solve for this term as well, the summation of the logarithmic differences, diba? Either by table or by using our own calculators, we already know how to solve for this term. Now, we just need to combine those two steps and we will be able to solve for the strength of figure problem. So, let's try, okay? We have our strength of figure sample problem here. But before that, I want you guys to remember the steps that we will be using. So, remember these letters, F, S, R. So, first step is, obviously, we need to find the strength of figure factor, the first value sa ato ang term. And then, we will find the summation values. And once we have F and we have S, we will be able to find R. So FSR, remember those three letters. So we have here our problem. Given the quadrilateral ABCD, assume that the observed interior angles have been subjected to station and figure adjustment. Okay, so okay na ta, okay? It has been adjusted. If all triangulation stations were occupied and all lines observed in both directions, determine the strength of figures and the length of the check base CD. So don't mind this part of the question yet. Let's focus on finding the strength of figures first. Okay, so this is our quadrilateral. And remember, the very first thing that I said in my part of the report, I said na in planning out the triangulation systems, possible na naay various positions available sa different station sites. So lain-lain nga mga routes ang pwede nato gamiton. And that's what we are going to calculate, or that's what the strength of figures are for, diba? So i-compare nato ang mga different positions na pwede nato gamiton, okay? So other than this sentence, the other given are, we are given the known line AB. So line AB, we have a distance of 1,586.85 meters. This is our known line, and this is our check base. So we will be solving for this later. And we also know that points A, B, C, D are triangulation stations. So this is our given. So we will first find the strength of figure factor, letter F, diba? Okay, so remember our formula here, diba? We just need to count what the value of our D is, the value of our N prime, S prime, and S, so that we will know what the strength of figure factor is, or our F, okay? So we did this shape ganina, diba? And we even calculated this earlier, and we got a value of F equal to 0.60. Okay, we solved this earlier. So now we have our strength of figure factor already. Okay, you guys, so this is our first possible route, triangle ABC and triangle ACD, with AC as the common side. Okay, so there will always be two triangles involved, and that's why it's chain of triangles, diba? So our first triangle is triangle ABC, this yellow triangle here, and our second triangle is triangle ACD, which is this orange triangle here. Okay, so unsa ganito tong button? Remember the logarithmic sign, diba? So our first angle, which one man? Since triangle ABC man, yellow triangle. Look at the yellow triangle. ABC. So our known side is AB, our common side is AC, diba? So our first angle nga ato ang that we will be looking into is the angle opposite to the common side, which is angle 43 degrees or angle B. So delta B mo ni siya ang ato ang first na angle na i-use. Okay, so log sign, let's input that in our calculator so that you guys will get used to it also. Okay, so and that should yield 2.258 or 2.257 times 10 to the negative 6. And remember, ato ang input is 2.258. Okay? So 2.258, we have that value here, and our second angle that we will be looking into is the one opposite to our known line, which is angle C here, 60 degrees. So delta C, diba? And we'll input that in our calculator. So our angle is 60 degrees. So and we just substitute that to our equation. Let's input this in our calculators. If you guys can input this just for checking purposes, we should get x equals 9.3. So this 9.3, this value is mo ni siya ang value sa ato ang triangle ABC, right? So triangle ABC pa lang ni. Kulangan pa taog value sa ato ang triangle ACD, which we will be solving later. I mean sa next slide, which is now. Okay, so triangle ACD is the orange triangle. Okay, so again, our common side is line AC, diba? And since wala naman diri ang known line, so what's the other line that we will consider? The required line, which is CD. So we have two lines here, AC and CD, ang relevant nga lines. So ang angles nga relevant are opposite them. So opposite angle AC, we have 36 degrees. And let's input that sa ato ang calculator. 2.897 times 10 to the negative 6. So therefore, our delta D is 2.898. Let's see, correct ba ta? Correct ta, guys. Okay. And next angle na relevant, di ba? Our required side is CD man. So the angle opposite that is 40 degrees. So we will input this in our calculator na po, delta A, because A man siya nga side. So delta A is equal to log sine 40 degrees, 0 minutes 1 second minus log sine 40 degrees, 0 minutes 0 second, and that should give us 2.509. So we now have values for our delta D and delta A. We will input these values in this equation, okay? We will input this in our calculator. It should yield 22. So what is our 22? Ano sa maning 22? This is the value sa kanisiya nga term sa triangle ACD. So remember, ganina atong gisolve is ang value sa ABC, and now we have the value sa ACD. So let's put that in our table para ma-visualize ninyo. First value nga ingani sa ato ang triangle ABC is 9.3. Second value sa atong ACD is 22. So we add that, kay diba naman to i-dere summation man tas ang we were looking for the summation of the values. So 9.3 plus 22 is 31.3. And if you can remember, since not na tayo summation, kani siya nga term, mumani siya ang summation. This one here, summation, that's this one, diba? And do you remember our value for F, this one? This was 0.60, diba? So 31.3 times 60, that should yield 18.78. So if you have trust issues, let me just input it here. 31.3 times 0.60 is equal to 18.78. Okay, so I hope na fix natin na inyong trust issues, guys. Okay, so let's move on to our second possible root. Dagat kayo ni siya. Actually, guys, we have 4 possible roots for this one. Okay, so we already solved for the first possible root, and now we will be solving for the second possible root, which is triangle ABD and triangle ACD. So triangle ABD is this blue triangle here, and triangle ACD is this green triangle here. The common side is, guess what? AC, diba? Obviously AD ang common side niya, this line here. Now we will be solving this one, angle D. Why? Because the known line is AB. So opposite that angle is 53 degrees. Muna siya atong first, and if we put this in our calculators, this here, aron, so that you guys will master it as well. Maybe if you guys will look at me, you will master it. Log sine 53 degrees, 0 minutes, 0 seconds. That should yield 1.586. Okay, there we go. Correct. And then our second angle is opposite our common side. So 43 plus 47, how much is that? 90. Okay, if you have trust issues with that, then you can solve that if you want. 43 plus into 2 is angle. So that should yield 90 degrees. So we'll just replace our angles with 90 degrees. And that's negative 5.10 times 10 to the negative 12. What does that mean, guys? This is times 10 to the negative 12. So, unsa naman na siya? 0.0000 something. Right? That should yield 0.01, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 5, 10. The definition ba is 6 place. So, 1, 2, 3, 4, 5, 6. And that's basically 0. Okay? So, our delta B value is 0. So let's substitute that in our formula. Here we have delta D of 1.587. Oh, sorry. This should be delta B. Okay, I'm sorry for that. Okay, delta D should be 1.587. There you go. We substitute that there and 0 here. So how much is that, guys? 1.587 squared. That should yield 2.519. So that is our X value. Okay? And now let's move on to our second triangle, which is triangle ACD, kaning grade 1. So this is the value, this is our value for triangle ABD, ang blue nga triangle. And now we will be solving for the green triangle. Again, 2 triangles, hence chain of triangles. So second triangle nato, first angle is 40 degrees because opposite sa ato ang required na line. So this one, muna siya 40 degrees. And that should yield, let's solve it again. Oh, okay, 40 degrees. How much is that? That's 2.509 times 10 to the negative 7. Okay, so that's there. And then our second angle is opposite our common line. So 60 plus 44, pila man na siya guys? 104. Yep, 104. So let's solve that here. 104, let's replace this by 104. There you go. And that should yield negative 5.249 times 10 to the negative 7. Take note of this, guys. That's times 10 to the negative 7. So that means dili 5.249 atong isuwat, okay? We will write 0.5249, okay? Or in our case, 0.525 because we rounded it up. And that is negative as well. So please really be mindful with the symbol or with the sign that will be yielded by our equation. So we have delta C of negative 0.525. Okay, so how much is that when we substitute that here? So if you guys can input these in your calculators for checking, we should get 4.702. Okay, so let's put that in our table para ma-visualize nato. So earlier we got 2.519 for our x, which is ang this value sa ato ang ABD. That's this one. And for our triangle ACD, we have this. So let's add both of those numbers, 2.519 plus 4.702. We will get 7.221. We multiply that by 0.60 here, and we should get 4.33. Now, I already solved this for you. If you want, you can try solving them at home and just check it with my answers here. I'm not going to go through all of them because we're running out of time. But as you can see, the smallest strength of figure value. So guys, remember, these values here, we multiplied it by our f, okay? Our f here is 0.60. All of these values, we multiply that by 0.60 and we will get these values here in a column. And our smallest value sa strength of figure is 3.70. Therefore, what does that leave us with? Remember, when comparing different values of r, the stronger figure has a smaller value. It means it is the root with the least error. Therefore, the strongest figure is the third possible root with chain of triangles ABC and, where's my cursor? ABC and BCD. This one here. Oh, sorry. Okay. So, mani siya ang ato ang triangle na strongest figure. So, this one, that's done. You already know how to do that. And now we can solve for the length of the check base CD. So, how are we going to find the length of check base CD? By the law of sine, diba? Using the law of sine. Diba? Mo man atong strongest figure, diba? Triangle ABC and triangle BCD. That's our strongest root. So, these are the two triangles that we will be using. So, we have line AB, we know what the length is of this one. This is given. This is 1.586. Pero for our second triangle, we don't know any of these lengths. We only know the angles. We don't know the lengths of these sides, diba? So we will use the first triangle for us to solve the second triangle. We know the value of AB. This is known, diba? BC, this common line here, BC over sine 77 degrees, gani siya, is equal to AB, which is known, over sine of 60 degrees. So, diba, this is the law of sine. You guys remember how to use this? This is the law of sine. And you just shift solve that, and you should be able to get a value for BC. See, let's solve for BC in our calculators. Do that. Okay, so our BC is 1785.37. So let's confirm that here. I wrote it here, okay? So now, nandun tayo value sa atong common side. And since it's our common side, so nana tayo value sa ato ang BC. And we can use again the law of sine to calculate for CD, which is our check base, which is our goal, diba? So, if we shift solve this one here, we will get 13.94. Again, if you have trust issues, let me prove that to you. Equals 1305.94. There you go, guys. We have our check base value. So we answered both of the questions now already. Congratulations! You guys now know how to solve for the strength of figures. You just have to remember these relevant formulas here, and you should be good to go. And if you guys have questions, please feel free to ask us here later if we still have time, or just message us on Facebook. I will be sending the table that we used earlier to the batch representatives, and hopefully they can pass it on to each of the blocks. Thank you guys for listening to our report. I hope you guys were able to understand all of the topics that we discussed today. We are just going to leave you guys with this verse from Colossians 3:23. Work willingly at whatever you do as though you're working for the Lord rather than for people. I know you guys have had a tough semester, and with online class going on, I hope you guys are still motivated. I hope in some way we were able to help you guys understand the topics that we are doing this semester. Have a blessed rest of the week.